Okay. So today what we will do is, we are going to revise what we know about LCAO and Huckel approximation and then we are going to talk about what are sometimes called term symbols. So it is going to be a revision of things that many of us know already, right, but we need this for the next stage. LCAO, Huckel approximation, and how to or what you can say is nomenclature of electronic states. I was tempted to get into electronic spectroscopy of things like benzene and all, but then I decided against it because that would be too much of a digression from what we want to do here. So tomorrow we are going to discuss naphthalene, which is a kind of a longish discussion. So what we will do is we will learn all that we can about naphthalene from symmetry. Okay. Yes, what did we do last day? We talked about benzene, isn't it? So, and then naphthalene is like a big brother of benzene, right? Two fused rings. How many p orbitals are there? 10 p orbitals, right? So we will learn how to symmetry classify them. I will talk a little bit about that today also, and then we will see what we can say about the MOs, what we can say about the energies of the MOs, and what we can say in a very preliminary manner about the spectroscopy of naphthalene, electronic spectroscopy of naphthalene. And then next week we go on to discuss, unfortunately we don't have time for too much of discussion, because last two classes I really want to derive great orthogonality theorem. So we will discuss maybe a couple of inorganic systems. We will talk about MOT as applied in inorganic systems. We will not get time to get into ligand field theory or crystal field theory as such. Okay. So I think everybody knows the meaning of this LCAO. What is the meaning of this? Linear combination of atomic orbitals. And as you know, this is perhaps the most primitive form of molecular orbital theory. What is a molecular orbital? A molecular orbital is analogous to an atomic orbital, right? But the only difference is that here you consider the joint field of more than one nuclei instead of one nucleus that you consider in, say, hydrogen atom. So the question is, how do you get the molecular orbitals? It is impossible to solve the Schrodinger equation except for one molecule. For which molecule can you solve Schrodinger equation and generate the molecular orbitals? No. Helium is not even a molecule. H2 plus. H2 plus, if you remember, is a hydrogenic system. Hydrogenic system as in one electron system, right? So for H2 plus, in principle we can actually solve Schrodinger equation and we can generate the molecular orbitals like what we did for hydrogen atom. The only difference is that instead of one nucleus, there will be two nuclei. So what complication will come in because of that? Rij? Yeah. What is Rij? No, that is easily done, but then there will be a more fundamental change in the approach to the problem. Internuclear repulsion, but then what I am asking for is even more fundamental. How do we solve? You are now going further and further away. No. What was the first step in the formulation of the hydrogen atom problem? What did we do? First step, of course, is to write Schrodinger equation. Then what did we do? We did some, yeah. No, before separation of variables. Okay, center of motion, you separated the motion of the nucleus. Then what did you do? No, hydrogen atom orbital, yes? Yeah, you convert it to spherical polar coordinates. Why do we convert to spherical polar coordinates? Because it is a central field problem. It is a central field problem, right? The attraction is towards the center. That is why you can use spherical polar coordinates. Do you think you can use spherical polar coordinates for H2 plus? No, because attraction due to this nucleus is there, attraction due to that nucleus is also there. So, you have to use actually what is called elliptical coordinates, which is bound to be a little more complicated than spherical polar coordinates, but it is still doable, but there is no need. What we want to do is, in any case we understand that whatever difficult formulation we develop using elliptical polar coordinates, that is going to hold for H2 plus and that is all, right. So, it does not make sense. So, it makes sense to go for the approximation right away, and the approximation that is simplest to use is that you consider that the MOs are made up of linear combinations of atomic orbitals. What is the advantage of this? The advantage is that it is a direct extrapolation of the valence bond theory that we are so familiar with. In valence bond theory also use atomic orbitals. What is the valence bond approach? You talk about overlap of atomic orbitals, right? Right? You say that one s orbital, one p orbital, another p orbital, head on overlap, that is sigma bond, side on overlap, that is pi bond. Is that right or wrong? Huh? So, you use almost a similar concept. What you say is that the molecular orbital is made up of a linear combination of atomic orbitals. You retain the concept of atomic orbitals because they are easy for us to visualize and understand, that is why. Okay. Now, so what you do is you write the molecular orbital, it is a psi k is the kth molecular orbital as a linear sum of the atomic orbitals phi I, right. Okay. Please understand that this is only an approximation. After class, Vibhav asked me last day, and then the thing is there was a talk last week about couple cluster theory and all. So, where the speaker said that there is no such thing as orbitals. Orbitals are used only for so that we can visualize, we can do things easily, which is a perfectly valid statement, right. But the point is LCAO is an approximation. Approximations are the way to go for complicated problems. As long as we understand that this is only an approximation, so it is going to work to a certain extent and no further, right. So, as we will see today and tomorrow, LCAO does work for some systems like benzene or for naphthalene, it works fine. You do not need more complicated theory for that. But if you want to talk about more complicated molecules, or when you want to talk about more complicated phenomena like excited state processes, their LCAO may or may not be sufficient. Usually it is not sufficient. That is when we invoke higher levels of theory. Even when you run Gaussian, you have to choose a basis set and you have to choose the level of theory, isn't it? So, generally what do? Do you start with the most complicated level? No. Why? Because there is no point in using a Damascus sword to shave, isn't it? If you want to shave, then a Gillette razor is good enough. There is no point of using a Damascus sword. If you have higher purposes, then you use the Damascus sword. Okay. So, what we would like to do is we want to stick to the lowest level of theory that gives us the right answer, right. And here our purpose is to see how by using symmetry the problem becomes even more simplified for certain cases, and we are going to restrict ourselves only for these benzene like systems, right, where you have pi bonds and the molecule is not very large. I just finished the response to the question you had asked after class yesterday. Fine. So, this is the approximation that we are going to go by for the purpose of this course. The molecular orbital is a linear sum of the atomic orbital. If you have a wave function, what is the next step? The next step is to write Schrodinger equation, right, in a simplest form. What is Schrodinger equation? H psi equal to E psi. But now the problem is we know that we cannot solve this equation. Okay. So, what we try to do is we try to manipulate this equation and we see if we can work around that problem and still find the values of energy. We have already approximated the wave function in a certain way. What is it that we do not know here in psi k? The coefficients. We do not know the coefficients. So, our problem is to find the coefficients and also to find the energy, alright, and we have to do it in a roundabout way, because this equation cannot be solved so easily. It is not going to be separable, unfortunately. Okay. So, you need a back door. So, what we do now is we look for the back door. Okay. So, what we do is, of course, you people are all masters of manipulation. You know very well that if you are given a problem, you have to subtract 1 from two sides, take cube root raised to the power of 2, and then take some terms from left to right, and then the actual answer arises. We are going to do exactly that. It is just that we do not have so many steps in this problem. So, let me write it like this: H minus E psi is equal to 0. I think you agree with me, right? No problem with that. Why am I writing it this way? Because by doing that, what I will do is, this is the first step of generating a system of linear equations. And when I generate a system of linear equations, I know how to solve it. How do I solve a system of linear equations? By Cramer rule, right? Cramer rule, secular determinant. That is where we are headed. Okay. Of course, now we have only one equation. We will see how we can generate many equations from there. So, H minus psi, H minus E psi equal to 0. What is psi? You can use this value. So, I can write sum over I. I will drop this k, right, and write Ci H minus E psi, no, not psi, sorry, phi I equal to 0. What is E? E is the energy of what? Psi or phi? Psi, do not forget psi. H psi equal to E psi, no? Not H phi equal to E phi. So, this E is the energy of the molecular orbital psi. Okay, fine. So, you have got this equation. Now, what do I do? First of all, let me write it in a little simple manner. Instead of, nobody likes summations, that has been established. So, let me take a simple situation where I is equal to just 1 and 2. I will work with 2 terms to start with, and then we will just write the other terms. So, C1 H minus E phi 1 plus C2 H minus E phi 2 is equal to 0. All right. So, from here I want to generate a system of linear equations. At least 2 need to be there, right. How do I generate that linear equation? In quantum mechanics, we always like to have triple products. Say multiply by phi 1 and integrate over all space. Then in the next step what we will do? We will multiply by phi 2 and again integrate over all space. That way what we are going to do is we are going to generate a lot of integrals, or in other words a lot of matrix elements, okay, and then we will work with them. So, let us see what we get. If you multiply by phi 1 and integrate, then what is it that you get? You get C1 phi 1 H phi 1 integrated over all space. Everybody knows bracket notation, you have told me, right? Multiply, then next term is against minus C1, E is a constant and so can come out, and what is the integral? Phi 1 integrated over all space. Okay. What is 1, what is 2? What is 1, what is 2? First atomic orbital, second atomic orbital of the same atom or different atoms? Different atoms, right. 1 is for atom number 1, 2 is for atom number 2. Okay. Let us be clear about that. These are not the atomic orbitals of the same atom. Otherwise, we can end in a little difficult situation. plus C2 multiplied by, you are multiplying by phi 1, isn't it? So, integral phi 1 h phi 2 minus E integral phi 1 phi 2 over all space. All right. Now, let us write this in a little short form. What is this integral phi 1 over all space? That would better be 1 than normalized. So, I write 1. What is integral phi 1 phi 2 over all space? Not necessarily. Not necessarily. That is why I asked the previous question. Do not forget that 1 and 2 are different atoms, right. If they are on the same atom, then the orbitals, the wave functions have to be orthonormal. But if they are not on the same atom, then they do not care about each other, right. So, my 1s does not have to be orthogonal to your 1s. Okay, they are in different galaxies, they are oblivious to each other. But let us think, what is it going to be? Is it going to be 1 or 0 or something else? So, this is one orbital, this is one orbital. Let us say the situation is like this. Then what do you have? You have overlap. Okay. So, what is that integral then? If this is what it is, this is one orbital, this is one orbital, that integral is just this area of intersection, isn't it? You are multiplying phi 1 by phi 2, right? At this point, for example, phi 1 has some value, phi 2 has no value, I mean phi 2 is 0. So, phi 1 into phi 2 is 0. Here again phi 2 has some value, phi 1 is 0. So, only in the intersection do both of them have some value, right. So, you have to multiply them and integrate over all space. What we are talking about is, we are focusing on this area, right. Of course, product integrated over this area. This is okay. So, what is this going to stand for? I think you know this already, but this is a concept where we sometimes falter. So, what would this integral stand for? Extent of overlap. S12, it is called S12. So, I can name this S12. What is this? Integral phi 1 h phi 1 over all space. This is called H11, and what does it stand for? Expectation value, right? Expectation value of the Hamiltonian for phi 1. What is this? It is called H12, and what does it stand for? Yeah. Suppose I say it stands for the interaction energy between phi 1 and phi 2. Does that sound right? Huh? That's kind of like the interaction integral, I can say. Exchange is right, but I like to call it interaction, because the moment you say exchange, this idea of this thing going there, that thing coming here comes, and that kind of becomes complicated. So, what I want to say is that this stands for the interaction between 1 and 2. Okay. Now, can you write this equation in terms of those nicknames instead of writing those full integrals? What is it? C1 multiplied by H11 minus E plus C2 multiplied by H12 minus E S12. Right? So, you have got one equation. How will I get the second equation? Right. I have only got the left hand side of one equation, now I have got the whole thing. How will I get the second one? You already said multiply by phi 2, integrate, what do I get? Work it out. And again write it like C1 multiplied by something plus C2 multiplied by something. Okay, this is the second equation, you can work it out. Is S12 equal to S21? Integral phi 1 phi 2 d tau would better be equal to integral phi 2 phi 1 d tau also. Alright. Now, so this is a system of linear equations in C1 and C2. Okay. When do we have non-trivial solutions? Secular determinant has to be equal to 0. Secular determinant is H11 minus E, H12 minus ES12, H21 minus ES21, H22 minus E. That determinant has to be equal to 0. Okay. What is this called equation? This equation is called secular equation. Okay. Now, and then I think in quantum chemistry or bonding course, you have studied of different methods by which you can evaluate this secular equation. Have you studied or no? Huh? How do I get H11 for example? See, what is the unknown in this equation? H11 comprises of two wave functions and the Hamiltonian. So, in principle they are known. If you do not even know the wave function, then what are you talking about, right? But do you know the wave function? Actually you do. In this case you are working with atomic orbitals. Okay. H12 minus ES2, there also H12 is an integral, you know the three terms, you know S12 also. So, the only unknown here is E. Okay. The question is, how do I know H11, how do I know H12, how do I know S12? How do I know them? Yeah? What is the energy of the orbital? Where is the energy of the orbital? This E is the energy of the molecular orbital. I am trying to find it. How will I know H11? H11 is integral phi 1 H phi 1. So, you can evaluate perhaps. If you know what is phi 1, if you know what is the Hamiltonian, writing the Hamiltonian is not impossible, right? You can always write the Hamiltonian, right or wrong. Whether you can use it and solve the equation, that is a different question, but you can write the Hamiltonian, and phi 1 is a relatively simple function. You can make this Hamiltonian operate on phi 1 and then left multiply by phi 1, see what you get. So, you can in principle evaluate the integral. Okay. But what I said of course is the rigorous pathway. Less rigorous pathway is that you can make an intelligent guess somehow or the other, and we will see an example of that intelligent guess in Huckel approximation. Be in no confusion here, LCAO itself is an approximation. Okay. Okay. We are working within the ambit of that approximation. What else can I do? I can compute. Even if I cannot solve, I can work this out numerically. I can see some of the people who are present here who know how to do it. Using a computer, you can do things numerically, right? Okay. So, I can do it numerically, I can guess, I can take it from some table, I can work this out numerically. But once I know these integrals, what I can do is I can expand this determinant. What will I get? What kind of an equation will I get if I expand this determinant? I will get a quadratic equation in E, right? And when I solve it, how many roots will I have? I will have 2 roots. Okay? So, those will be the values of energy. Alright. So far what have I used? I have used the atomic orbitals and I have used the Hamiltonian. What I have not used is the actual molecular orbital. So, see, even without using the molecular orbital, one can in principle work out the energy if you can have some idea of these integrals. Alright. What will be the next step? Now, see, look at the first equation. Suppose you can solve this equation and get the value of E. You get 2 values, right? 2 roots here, E1 and E2. So, what you can do is you can put in E2, E1 here, put in the value of E1 there, okay. Then you get a simple equation in C1, because if you can reach up to E1, that means you already know what is H11, what is H12, what is S12. Okay. You just put in E1 in both the equations. Now, it becomes an equation in C1 and C2 that you can solve. You solve that and you find what is C1, what is C2. Once you know what is C1, what is C2, what is it that you have worked out? The molecular orbital wave function, psi. Do not forget, psi equal to C1 phi 1 plus C2 phi 2, right? Yes. E is unknown, that is what I am saying. What you do is you find E from solving the Schrodinger, the secular equation. We are finding out three unknowns or more unknowns, actually 4 unknowns, 2 values of E, do not forget, from a system of 2 linear equations, okay, which sounds counterintuitive per se. But the only reason why we can do it is that we are saying that we know the values of H11, H12, H22, etc. Okay. So, that is the power of your Cramer's method. So, first work out E, then insert the values of E here and then work out C1, C2, and you can do that for E1 as well as E2, right? Understand? So, now see how many wave functions will you get? You will get 2 wave functions. One with the lower energy will be called the bonding molecular orbital, one with the higher energy will be called the anti-bonding molecular orbital. Alright. So far so good? Yes, sir. Yes. Yes. Talking about normalization, normalization becomes very easy in Huckel approximation, but not here. Yeah. You have another equation by which you can find normalization constant, that is right. But the problem is that normalization constant will come outside, right. So, when you equate it to 0, the normalization constant goes. That is why we cannot use it, you have to do it this way. Okay. I think you have all read it somewhere or the other. I am just recapitulating at a very easy pace, so that tomorrow when we talk about naphthalene, we are all very comfortable. That is the reason. Okay, this is fine. You can find out not only the energy, but also what the molecular orbital looks like. Okay. What is the basic assumption? See, it is not as if we are doing it without an assumption. We are doing it with the assumption that we know what is H11, what is H12, what is H21, what is H22, what are the overlap integrals. Only with that knowledge can we use this method.